Good afternoon. Welcome to Session D, Concurrent Session 5, Emerging Technologies in Safeguards 1. Let's get into the presentations. I am Christopher Ramos, the Safeguards Research and Development Portfolio Manager. My presentation will cover recent progress in the Office of Defense Nuclear Nonproliferation Research and Development initiatives in data science for nuclear safeguards. I will begin by introducing our office. The mission of Defense Nuclear Nonproliferation Research and Development is to drive innovative research that develops technologies and expertise to detect nuclear proliferation activities and produce technologies for integration into operational environments. We do this by leveraging capabilities across the national laboratories, plants, and sites, and collaborating with universities and private industry. Within the Office of Defense Nuclear Nonproliferation Research and Development is the Office of Proliferation Detection, whose mission is to develop U.S. technical capabilities to detect, prevent, counter, and respond to nuclear security threats by investing in research and development at the Department of Energy National Laboratories. The Office of Proliferation Detection is divided into 3 teams: Material Production Detection and Monitoring, Nuclear Weapons Development Detection and Material Security, and Non-Proliferation Enabling Capabilities. Nuclear Safeguards Basic Research and Development falls in the Material Production Detection and Monitoring team. The Office of Defense Nuclear Nonproliferation Research and Development is the leading U.S. government organization for development of new technology in support of the U.S. government nuclear nonproliferation goals. Success with our broad investment portfolio relies on teamwork between headquarters and our exceptional national laboratory workforce. An example of that teamwork that I will showcase is a multi-lab project that deals with innovations in data science, specifically for nuclear safeguards. Nuclear safeguards is a data-rich field ideal for the application of modern data analytics techniques. The goal of the work presented here is to show a path of data science technology maturity that has potential applications in U.S. domestic and international nuclear safeguards. Multidisciplinary teams at 3 national laboratories are working together to advance a suite of data analytic capabilities to support safeguards activities at declared facilities. The multi-lab collaboration is leveraging heterogeneous data streams from NNSA testbeds for developing and evaluating approaches. The outcome will be a set of unique peer-reviewed studies aimed at better understanding 3 key questions. Can the data be trusted? Data assurance. Is it useful? Signature discovery. And how can it be interpreted? Patterns of life. Each of the questions above is addressed by a data science topic area and is investigated by the labs in a joint effort to develop advanced data analytics techniques for safeguard-specific applications and determine their utility. The Sandia National Laboratory teams are investigating data assurance in 3 key areas. The first is anomaly detection by grammar compression augmented with ensemble learning. The second is developing secure data transfer in a multi-party computing environment with garbled circuits. The third is developing and testing a novel safeguards data authentication, integration, and analysis workflow based on distributed ledger technology. The diversion of nuclear material or misuse of a nuclear facility is likely to manifest itself as subtle aberrations in a set of normally repeating patterns in a safeguards dataset. To detect these subtle changes, the Sandia team has been investigating grammar compression augmented with ensemble learning to detect multiple variable length anomalies all at once. The process to do this is called grammar induction, where you prepare a symbolic aggregate approximation in 4 steps. First, you convert the input time series to a discrete sequence of symbols with a sliding window. Second, you apply grammar induction to the discrete sequences to identify grammar rules that are repeating strings of symbols. Third, map the repeating strings back to the subsequences that the strings represent. Fourth, compute the rule density curve, which is the frequency of rules at each point. Assuming anomalies correspond to rarely occurring strings, they will be minima in the rule density curve. When the grammar compression method is combined with ensemble learning, that is taking advantage of the idea that many members of an ensemble can be wrong, but since errors are random, they should cancel over a large enough ensemble, resulting in enhancement of the correct outcome. Here is an example dataset of an electrocardiogram and its rule density curve, initially representing dense regular data and a steady rule density curve. As the data go off normal, you can clearly see a minimum in the rule density curve. As the data begins to recover, it starts to look more normal and regular, but still contains abnormalities in the rule density curve. The team continues to refine grammar compression augmented with ensemble learning to make a robust data anomaly detection method. Multi-party computational data streams can complement traditional safeguards data obtained by inspectors, resulting in a potentially larger body of data to which safeguards-focused data analytics can be applied. The underlying concept is that two or more parties can ask a question involving sensitive data and receive an answer without revealing to either party any of the underlying data. Privacy is easily preserved using a garbled circuit as the primary multi-party computation. The research team has successfully developed a simple prototype garbled circuit tool to guide the development of more sophisticated real-time analysis methods. This method is intuitive with straightforward implementation, transparency for each party, and efficiently can run online in real time and enables fast computations. The path forward includes enhancing the speed of the Cipher circuit library and construction of a more realistic safeguards-relevant data circuit applied to data from NNSA testbeds. The technology developments will allow nuclear facilities with different data sensitivity concerns to share data amongst themselves, potentially across borders, enabling safer operations, more transparency, and offer confidence that participating facilities are being used only for intended purposes. The fact that individual facilities or states manage non-IAEA safeguards-relevant data at their discretion opens an opportunity to investigate distributed ledger technology as a platform to encourage the standardization of record-keeping. The Distributed Ledger Technology Platform introduces benefits such as ease of auditing, security against forgery and tampering of data, decentralization, and assurance of continuity of knowledge. As an example, a distributed ledger for UF6 cylinder custody has the potential to provide real-time accountancy of the custody and the state of UF6 worldwide without mandating trust in a single data custodian. The current research efforts are developing distributed ledger technology methods on safeguards-like data generated from an NNSA testbed to demonstrate the security, accountability, and cost-benefit analysis of deployment as a pilot method for data handling. Anomaly detection, data privacy, and data provenance are key aspects of developing trusted data sources in the safeguards community. The data analysis assurance work accomplished by the Sandia team will be coupled with signature discovery and pattern-of-life analysis methods being developed by Oak Ridge National Laboratory and Los Alamos National Laboratory to build a unified safeguards data analytics toolset. The Oak Ridge National Laboratory is exploring signature discovery, drawing upon their novel capabilities in data analytics and experience operating the high-flux isotope reactor and the Radiochemical Engineering Development Center. They are identifying high-value data streams to aid the development of future detection equipment that will improve safeguards in states with research reactors and radiochemical facilities. They refer to this as using real data to get real answers. The ORNL team has developed a methodology to translate safeguards-relevant questions to ones that can be acted on by statistical tests. The further development of this testing framework will be used to answer safeguards questions and evaluate which data streams provide the most value in drawing robust safeguards conclusions. The three signature discovery research goals are to 1. Deliver a generalized evaluation approach that translates safeguards questions for a facility into specific testable metrics that measure the performance of data analytic methodology when applied to any nuclear facility's safeguards approach. 2. Provide a data analytics method that has the potential to improve the robustness of the examination of operator declarations for high-flux research reactors coupled with radiochemical facilities. And 3. An evaluation of the highest impact data streams for drawing safeguards conclusions in a research reactor and radiochemical facility. Applications of this work to nuclear facility operations include analyzing core average burnup from sparse sample sets and developing a polycotomous classification modality for the relevance vector machine methods used to analyze simulated list mode data, consistent with the modified JCC 71 neutron color, to identify off-normal fuel rod configurations and localize missing fuel rods. The signature discovery work also includes using mock erroneous entries introduced into the landmass data to explore how well current methods detect errors using random grid replacement to generate errant data. Creating a data analytics performance evaluation framework. Selecting events of interest and identifying their data streams, like accounting for uncertainty and noise in radiochemical assay, and testing of advanced statistical analysis on radiochemical assay in the SF-Compo database, and creating 2 new methods for looking at transactional data from landmass using network graph analysis and principal component analysis, demonstrating a proof-of-principle method for examining transactions and their underlying nuclear material process operation. This work by Oak Ridge National Laboratory advances mathematical analysis tools for signature discovery, providing the safeguards community with a robust data analysis toolset that will give plant operators and inspectors deeper insights into operational issues that will help verify that research reactors and nuclear chemistry reprocessing plants are being operated in accord with the peaceful uses of nuclear science. The Los Alamos National Laboratory is investigating data analytics for improving the efficiency and effectiveness of safeguards verification by examining patterns of life, testing the hypothesis that in a single-purpose facility, signs of life reflect the activity associated with the facility purpose. This is done through the evaluation of supervised machine learning methods that automatically integrate disparate data streams generated at Los Alamos' Technical Area 66 Safeguards Training Facility. The expected outcome of this work is to provide decision support tools to the safeguards community to increase both the productivity of its operators and the probability of detecting material diversion or misuse of a safeguards facility. Safeguards relevant data streams were chosen that are compatible in nature to what the IAEA currently collects, including neutron singles and doubles, which are like NDA verification data. Badge reader information is like CNS data, material movement logs are like material accountancy data, and sensors distributed throughout the facility are like CNS data. Over 200 days of data have been recorded, generating over 100,000 pairs of features, and approximately 1,600 pairs having a correlation greater than 0.75. The worst data features identified do not appear to carry any useful information. However, every good feature did improve classification results. This classification and analysis scheme resulted in the ability to distinguish weekends, weekdays, course days, course preparation days, and holidays in the data streams. The Los Alamos National Laboratory team demonstrated the fusion of data sets using machine learning methods to integrate persistent, heterogeneous data that characterize patterns of behavior at a known facility. This brings the safeguards community closer to the goal of facilitating automated detection of facility use or misuse in order to verify that nuclear material diversion is not taking place. This multi-laboratory effort seeks to apply advanced technology in the field of data science to closely examine traditional and non-traditional data relevant for generating robust safeguards conclusions. Areas investigated include data assurance, signature discovery, and patterns of life. The combination of the advanced data techniques developed from this work will provide new, secure, more transparent options and tools for the nuclear safeguards community. I encourage you to see the team talks throughout the meeting.
What will they think of next?
I don't know, Inspector, but I do know this work brings us closer to our vision of unobtrusive surveillance with instantaneous accountability.